Bismillah ar-Rahman ar-Rahim. Good morning. Today I'll try to summarize the Hooks Law experiment and create strong link with all of these two sides, theoretical and experimental side of this experiment. I'll try to do that during 10 minutes. Let me start. Here I have two goals. The first one, the general one, all the students should have the ability to create strong link with the all of these two side, theoretical and experimental side, to an experiment, sorry, okay? Not just in this experimental Hooks law, experiment Hooks law. And my goal during this video will be to verify Hooke's law and to determine the force constant of the spring related with this one. Here, let us think about this picture. What is the difference between these two springs and with this one? This is smaller one according to all of these two. Sure, the cross section area is different. And let's think about uh, what about the another difference, like, or it's scientific, more scientific. We will say the K constant of this spring with the bigger cross area, it's much than the others. Okay? We will explain that deeply. At first, let's verify Hooke's law. What is the Hooke's law? Hooke's law form F, that means force, with n unit, equal K, that means the K constant of the spring or to another, and the extension, E, the first letter from extension. What that means, the minus here, the minus that means the restoring force direction of the spring. It's opposite with the gravitational force. When I put mass or weight or force to stretch this spring, will be at tensile force. This kind will be the tensile, will be with the same direction with the gravitational force. By that, the restoring force will be up. That means with the opposite direction with the gravitational. By that, this is a sign to this opposite direction. Here, you can calculate the K constant. I need this column, this diagram. Here, every 102 something gram, approximately 1 unit. If you want to be sure and uh, you know how we can calculate, if you want to know how we can calculate it, all this newtons by 1, 2, 3, 4, 5 units and newtons equal what? You can take a look to you can scan this barcode and you will see everything related with this experiment. Let me come back here. Weight 100 gram equal length of the spring, the original length here. When I put some mass or weight, what will be? That's L2. The extension is L2 minus original length. Here we have diagram F, the force with unit with Newton at x-axis, extension with centimeter. I prefer to be with centimeter, at y-axis, the relation will be linear relation between them. That means we can calculate the slope. Why we need slope calculation here? Let me prove that by verify Hooks law F equal K extension. By that, K equal force divided on extension. Slope from tan theta equal extension divided on F. By take a look to equation 3 at 2, we will have this conclusion to K equal 1 divided on slope. By that, slope calculation is very necessary to can calculate the K constant. Here, the link of my experimental results, how I could to measure the necessary results to another spring, not this one. It's just to an example. Uh, how I can, how I could calculate all the results by using another spring with different masses, like the written at the column, obvious column. Here my result, the extension. Let's plot them. Will be like that. I calculated the slope. It's approximately 2 dot something. The K constant equal less than dot 5 Newton divided on centimeter. Okay, less than. What that means? Let's think about that. What that means? That means I need less than dot 5 Newton to make extension to 1 centimeter. If I need extension to 10 centimeters, that's mean I need 5 Newton. Okay, 5 Newtons. And it goes like that. If you want Newton, if you want to know how much Newtons you need to stretch the spring to 1 meter, for example, okay? From the curve, the relation between the extension at y-axis and the force at x-axis is linear, and that number means. Here, you can scan this barcode to take a look, to watch all my solved example, okay? How I converted the grams to newtons and the other details. Here was the relation between these two pictures. Actually, every iron bar, material bar, plastic bar, any material bar has the same properties. Actually, at first, from this diagram, will act as a spring at the elastic region. Okay, but here it's measurable, seeable, visible. Here it's not visible. It's difficult to. We need very high quality high camera with high quality to measure that. By that, from O to A, any material bar will act as a spring. Okay, at elastic region, when unloaded, the mass will come back to its old shape, original shape. After that, to be, and when the force will be more than, the shape start to change to D. Some fractures will happen. At E will be to two parts. Okay, here we prove that by plot the relation between them, and we prove that the relation between them is linear. What is the link with the medical physics? All of these previous information related with physics department. At medical physics, any material bar will a huge ability, a huge similarity. The same thing with the bonds when acted to mass, to weight, to force. The same diagram, but just here it's converted to be bonds, stress, strain stages of uh, material bars. It's be here of bonds. The same diagram with the same names, same stages. Okay. Review about Hooke's law. We proved that this part by plot the relation between weight and extension. We prove that the relation between them is linear. We calculate the k constant and we understood what that means. And after that, we did our link with this diagram to say any material bar has the same quality, the same properties about the ability with the external force to tensile it by mass, weight, force. And here, the great thing is any bar has ability to take most of the force, or let me explain that by if we need 80 newtons, for example, to make this material bar to be two parts, maybe at 6 newtons, according to the bar quality, we will be at the safe side. What that's mean? At elastic region, when I unload it this way, this force, this bar will come back to its shape or will be without any shape difference. But by increasing a little bit, will go from B to the another point, this the C. By that, the first shape difference is started. Maybe here it's 8, it's enough to make this part to be two parts. But for example, approximately it's here, it's 6. 6 with the safe side. More than what I wanted to say, the great quality, the great property to this bar, to this bone, it can take most of more than the half of the necessary force to make it to be two parts with no differences at elastic region. That's it. My lecture is done. See you in next one. This video is different from the previous by using some barcodes uh, to make my students has ability to scan these barcodes and go to another video to another information source from the same video. That's it. See you in next video.